Hello and welcome to this, our 16th talk on time, the physics of time. Today we're going to talk about why doesn't academia accept the logic of what we're talking about? And actually we and the academia do accept the data. Where we differ is in the interpretation of the data. Well, many people will think of physics as being pretty cut and dried. It's the ultimate of, you look at the logic and you have rigorous math equations to produce numeric answers. It's all driven by the empirical data. How could physics academia, the very smartest people in the world on physics, and for well over 100 years, be advocates of special relativity, and yet have special relativity wrong? You may have been listening and saying, okay, I see what you're saying, nick of time, but I just can't get over that obstacle. Well, this is to give some insight into what may be happening. And it's a very interesting topic in general anyway for all of science. And this will not be just a listing of common sense items or theoretical items, but rather these all come from my personal observations, having been working in interacting in the trenches on this very topic, a lot of it on the twin paradox debate, for over 50 years. And when you are in a debate with someone for years back and forth, then you begin to be able to see inside the mind as to what's going on. Now, admittedly, this is not really a discussion of physics per se, but rather a discussion of human psychology, except for at the end where we discuss the special relativity time dilation equation and some characteristics of it. So feel free to skip this talk and return next time for a discussion of general relativity and time. But if you're skeptical about what we've been talking about, it might be worth getting this different perspective. And as I say, I think it's a very interesting topic in general. Okay, the first reason it's chosen based on the chronological criterion. Why did special relativity get accepted in the first place? Well, at the end of the 1800s, Lorentz ether theory and ether theories in general were well accepted. But they became out of favor because neither the ether itself nor a good candidate for an ether frame could be found. Further, when the Michelson-Morley experiment seemed to show that the Earth was not moving through an ether, and Lorentz came up with what I term as Lorentz relativity, that seemed like an ad hoc fix to his theory. Let me talk about LR, Lorentz relativity, for just a second. If you take special relativity's time dilation equation, and you just have what used to be in special relativity relative velocity, and replace that with absolute velocity with respect to some preferred frame, which in the Lorentz ether theory would be the ether rest frame, then you'd have Lorentz relativity. Now, I'll come back to this point later, but anyways, this was how academia reacted to those two problems. Academia liked special relativity because there was no ether, and there didn't seem to be an ether. At least one didn't seem to be able to locate it, get evidence for it, or understand where the ether frame would be. Furthermore, special relativity seemed to be built on a fundamental principle, namely the relativity principle. And the relativity principle was a principle in good standing for several centuries in the area of mechanics. So it had a great appeal to academia, and that's why it became adopted by academia over ether theories. Now it's interesting, we'll get to this later, but one of the major things that caused special relativity to be accepted was when Arthur Stanley Eddington went to Africa, observed a solar eclipse, and alleged that the data showed that light from stars bent around the sun in exactly the way predicted by general relativity, and that caused a media sensation and acceptance of general relativity, which in turn caused acceptance of special relativity. That was around 1919. Later, when people examined the raw data, they found that, to put it nicely, Eddington had done some cherry picking because a lot of the data didn't agree at all with general relativity, and some seemed to agree, and he chose just to present the latter. So we're getting a feel for some controversy here right from the start. Okay, we'll talk about belief systems. On the one hand, academic professors are usually very smart and have a strong aptitude for physics and logic and math and all that. But they are human. And once a strong belief system has been established, it's hard to break, no matter what field you're in, if you're human. And all that reinforces that belief system tends to be accepted without really critical analysis or critical thinking. And all that challenges that belief system tends to be rejected out of hand, again, without critical analysis or critical thinking. So strongly held belief systems play a big role. And again, let me emphasize, I'm not saying that physics academic professors are unusually prone to this problem. I'm saying this is human. This would be equally true of, say, a so-called dissident physicist who is disagreeing with currently accepted theory and has painstakingly created an alternative. Then he's going to have a strong belief system about his theory and be very resistant to throwing it out. And certainly true of myself, having worked for not only years but decades in my examination of special relativity. That has now created a strongly held belief system here. So we're going to ask you to exercise your critical thinking. Further on belief systems, we have Professor Peter Hayes, and he writes that in his analysis of the twin paradox, for physicists to ignore the considerable evidence against special relativity's time dilation being interpreted as it was for the twin paradox smacks of special relativity having become an ideology as opposed to a topic in science. Other observers echo Hayes's contention above and contend that relativity has become a philosophy and or a religion. And no progress will come until one of the high priests of physics recants. And again, this is nothing specific to physics professors. This is just how the human mind seems to work. And quite frankly, there's very good value for that, because a single human, no matter how smart, is limited in what he can achieve. You can't build a skyscraper or a particle accelerator for that thing, or a ship that goes to the moon. A single person can't do that. Humans have intelligence, but they also can work together in very large groups and come up with a single goal. But that means keeping your focus on that single goal and all of them keeping that focus on that single goal for a considerable period of time. So there's great value to having strongly held belief systems that are hard to overcome. Okay, now the issue of identity and one's ego. Being a relativity professor is high prestige. We hear people talk about a rocket scientist. Well, being a relativity professor is even higher on the scale of awe about great intelligence in the public's mind. So relativity for physics professors often becomes a part of their identity, his or her identity, and their ego. Can you imagine having taught and written about relativity for, say, 30 years, and then having to say, oops, that was a little big mistake, sorry. There's going to be resistance to that. And again, peer pressure, another thing common to humans. Physics professors are human and subject to peer pressure, as in any social group. And related to that is groupthink. You talk to your buddies all the time, and you tend to think alike and have the same idea, and the group thinks as a single person. Well, Harry Ricker mentioned, well, science should not be just about focusing on a single theory, on just currently accepted theory. I mean, it doesn't make sense in general. You don't. For politics, it hasn't really worked out to have a single party like communism, or in economics just to have each industry controlled by a monopoly of one company. That has not turned out very well. You need competition of ideas and different thinkers, and let the best ideas prevail. There's no reason why science should be the one thing where you can only think about one topic, one solution. This is big. The empirical data is the erroneous belief that special relativity has been proven by the empirical data to 9 decimal places. And I've heard that specifically said in those ways. For example, Professor Edwin Taylor, who was nicknamed Mr. Special Relativity, was co-author of a book called Space-Time Physics. And for edition 2, he asked William Shercliffe of Harvard, who ran the Cambridge Accelerator for a long time, to review the book. And since Shercliffe and I had been debating about special relativity and had seen various flaws in it, Shercliffe said to Taylor, well, why don't you have Nick of Time review the book as well? And I did, and we got back his comments and reactions to our different inputs, and some were accepted that this was not changing the interpretation of special relativity, which is on readability and whatnot. But I noticed, I mentioned to Shercliffe, I said, well, you know, he's commented on everything, why he's rejected and why he's accepted, but he didn't say anything about my comments on the twin paradox and why it didn't make sense. His explanation of swinging lines of simultaneity. And Shercliffe, who knew Edwin Taylor very well, said, Taylor believes and has said that special relativity has been proven by empirical data to 9 decimal places. So any criticism of special relativity just would be a waste of time to look at because it's been proven. So he never even looks at arguments about the twin paradox. So that's a little interesting anecdote that hopefully will give some meat to what we've been talking about. But let's look at this. Let's apply a little critical thinking here. Let's look at the data. Well, here's the special relativity time dilation equation, and the single variable is V, because C is a constant. So the rate of time depend on 2 different inertial frames, and special relativity is a function of velocity squared, really. But that's relative velocity, the relative velocity between 2 inertial frames, any 2 inertial frames. But the data that agrees to 9 decimal places also would agree with Lorentz relativity, because they're same equation, except that for Lorentz relativity, V is velocity with respect to a single preferred frame. So if that's where velocity is being measured from, then the data is also in agreement with Lorentz relativity. So one has to be careful, or you have to apply critical thinking. And you can see how some people have just closed their mind because they're just so sure that special relativity is correct. Sometimes for the very reason I stated at the beginning, we need to be careful about accepting special relativity without thinking about it. And here's one of those reasons. Firmly held, but not well grounded. Okay, let's also look at another aspect of the empirical data that academia thinks has proven relativity. Well, when testing currently accepted theory, relativity and other science theories, many factors favor finding confirmation of the accepted theory. Often, it's the criterion for claiming that the experiment, the data that the work that someone's doing is a success. If you don't confirm it, then you fail to confirm it. Further, there's another factor, particularly in this age of high technology and billion-dollar equipment and experiments, for the discovery of the Higgs boson, for wrinkles in time by George Smoot, like gravity waves being discovered, allegedly. Tons of data are created and then sifted through by supercomputers. And then further, so-called noise is removed by softwares. So all the things that wouldn't fit with what you actually look for are removed. And then you've got a ton of stuff to search through. And if you don't find it at one level, then you can try and look at a much deeper, at a much finer grain level. And as someone commented, using this technique, you're almost sure to find whatever it is you set out to look for. And finally, if you're doing an experiment to find something and the data comes in and the data is too high to really confirm accepted data, the tendency will be to say, oh, I must have made some error. Let me look for a source of error that would make the data come out too high to confirm the theory. And then you look very hard for something that would make the data come out too high, and then you find it and say, oh, here's the error I made. Oh, come with me. And you take out that source of error data, and by golly, that you've come very close to confirming currently accepted theory. Just as an incident, I've looked very carefully at Wrinkles in Time, which is written by George Smoot himself. It's going to be written to make things look good, but I see this factor. And Professor Unziker from Germany, I looked very hard at analysis done for the discovery, the alleged discovery of the Higgs boson, and again saw the same thing, even though there were two very different experiments in really different fields of physics. Okay, a third item on the empirical data. When the empirical data does not match currently accepted theory, theory is not rejected, but rather it's extended to bridge the gap between the data and the theory. Now, let me say that I'm not saying that this is a horrible, terrible thing to do, because, quite frankly, this is what Lorentz did with his theory. The data from Michelson-Morley didn't match what was expected, so he extended Lorentz ether theory with Lorentz relativity theory and added such things as length contraction and clock retardation. And I think he got the right answer when he did that. So I'm not saying this is terrible. I'm just explaining why rejection of special relativity has not occurred when we have the logic and I believe the empirical data saying it needs to be rejected, at least the interpretation that we've been talking about physical clock slowing. Okay, examples of that first bullet would be the creation in physics theory of dark energy and dark matter, which now fills 95% of the matter and energy of the universe. That creates what I consider to be a dark age of space-time physics. It's built on fudge factors. In fact, we could call them dark fudge factors. And sometimes you might see a headline saying, dark matter confirmed. Well, if you need to add dark matter to your model of the universe to explain the rate of rotation of a spiral galaxy in one spot of the universe, then it makes sense that if you're going to look at another spiral galaxy, you'll need to do the same thing. So that doesn't, the fact that you need to add in this dark fudge factor doesn't verify that dark matter exists. It just shows that there's going to be a gap between data and currently accepted theory, and it either has to be filled with dark matter or dark fudge factor. And I say there happen to be one and the same. Another example of this tendency to bridge the gap between data and theory is the Big Bang theory of inflation. Now, the current Big Bang theory is built on general relativity, and the data, there was a problem. The universe was not as homogeneous as theories seemed to call for. So inflation was created to bridge the gap between the data, the empirical data, and the theory. Well, inflation, in the context of Big Bang theory, requires the universe to expand by a factor of 10 to the 78th. That is a huge number, beyond comprehension, really. It's not just a number of all the grains of sand on the Earth. It's pretty close to the number of all the particles in the entire visible universe. And it did that humongous, incomprehensibly large factor of expansion in less than 10 to the minus 32nd second, which in turn, that's an incomprehensibly small amount of time. 1 divided by 10 followed by 31 zeros. I mean, that's huge. A huge expansion in an incredibly short period of time, and they don't have a really credible explanation of why inflation started or why it stopped. So, bridging the gap between theory and data by adding something can be good, but I think in this case the tendency just tends to go overboard and tends to just work to save a failed theory or a theory that has problems and needs fixing in other ways. And just very quickly, obviously, being a physics professor, being in physics academia, that's your career. When you're young, you don't want to do anything to rock your boat. You need to establish tenure, and I misspelled career here. That's your salary. That's where it's coming from. You don't want to rock the boat. You write textbooks, and that gives more money. So that definitely is a factor in wanting to stay in the club and not be a heretic, not be kicked out. You know, there were people like Herbert Dingle, and when he said, here are some problems with special relativity, basically he was tarred and feathered and ridden out of town on a rail, out of academia on a rail, and called the quack. And you know, he had tenure and all that. And you know, we have job security within CNPS. We have some people who are in physics academia and who challenge currently accepted theory, and physicists who held positions in the government said that this is not acceptable. This university is not going to get any more money unless this person gets fired. And you know, there are several people who've been fired for challenging currently accepted theory. This is a genuine retardant on rejecting things like special relativity. There are other reasons, many other reasons. One really is that special relativity is not well defined. So if we find reasons why one interpretation of special relativity is time dilation, has major problems, someone else, they can go to another interpretation, say all is well, you know, we'll just interpret it differently. And I've seen many people who are ardent relativists, and they might say, well, special relativity is right, but it needs to be modified, that the mainstream isn't, the rest of the academia isn't interpreting it right. They need to get rid of relative simultaneity. Well, I agree with that. I agree with that. But if you You can't really keep special relativity and get rid of relative simultaneity. That's part of the heart of it. Such people probably have taken the first step in applying critical thinking and eventually will come up and be critiques. But it takes time. It takes thinking. It takes, if you have a strongly held belief system, there's a lot of inertia to that belief system. But there tend not to be revolutions in your thinking, but it needs to evolve over time. And that progress in that evolution is retarded if you're in an atmosphere of groupthink where everyone else is singing out of the same hymnal and in disagreement with you. Other people, I'm thinking of one person in CNPS right now who says special relativity, or thinks special relativity is right. I mean, this is just part of reality. So, therefore, by necessity, all criticisms of special relativity must be wrong. As I say, when you talk to someone for years about it, you eventually can see what's going on in their mind. And a lot of physicists say, well, the math of relativity is really beautiful. And one of our first point was that it had a great deal of intellectual appeal, allegedly being derived from first principles, such as the relativity principle. It has a great of academic and intellectual appeal. So there were a lot of different factors that would keep someone thinking that special relativity is right, even when they're presented with something that normally would cause them to say, oh, here's a problem. Okay. Hopefully that gives you an idea of some of the problems. And again, we have a picture to try and keep this in mind. Here's Professor Jose Lopez, who says, critical thinking today is a difficult undertaking, but we should keep fighting to restore critical thinking. I am with the campaign to restore critical thinking, and the campaign to restore critical thinking is a campaign of the CNPS. Again, I'm a member and director and an officer of that organization, worldwide organization of physicists, many physics professors, PhDs, and independent researchers. And here the picture, perhaps unkind, is showing a whole group of people who think alike, pictorially represented here, and who have an old idea of a candle flame. A person comes up with a new idea of having an electric light bulb, but they're apparently thought of as a heretic, so they're led to be hanged. And this is the picture to show why we need to accept critical thinking. Well, that's the end of this talk on what, again, I think is a very real problem and has been over the centuries. For example, in geology, the idea that the continent was fixed was initially challenged 400 or 500 years ago, but it went for at least 400 years not really being seriously challenged in geology academia, who were really the last ones to accept the fact of first continental drift and then plate tectonics shifting. So it is a big problem. There is inertia once you've had ideas that have become belief systems. Okay, we will continue with our physics discussions of time next time when we talk about general relativity and its constructs of time. Thank you very much for joining me. Hope to see you next time.